students. Today we're going to be looking at speed, reflection, and transmission of waves. One question I have for all of you is, have you ever been to a pool before or even a water park, the ocean? What happens to the waves as they hit against different barriers, the edge of the pool, for example? We're going to take a look at some of these questions that you may have. I hope that you're also following along on your notes too. So the first thing is that a reflection basically is the return of a pulse in a wave from the boundary of a medium. So it hits a different medium, so something that's either going to be a little bit more dense or a little bit less dense, and it then reflects in the opposite direction that it was once going. We also have two different options, and we actually looked at this the other day through that app. And so the first one was the fixed end reflection. And we might not have focused specifically on all the interactions. We were looking more at what the names of the different parts of the waves were called. But in a fixed end reflection, you're going to have one part that's just going to be stationary. A fixed end exerts an equal but opposite force to the pulse. And the pulse is reflected on the opposite side. And so we're going to take a look at that in just a moment too, what that actually looks like. On the other side, the free end reflection, that's the one where the particles of the medium exert a force in the same direction as the pulse. And what ends up happening is that the pulse is reflected on the same side. And so we're also going to take a look at what that is as well. Reflection off a solid fixed surface can look kind of like this. So first of all, you're going to have your wave drawn like that. And once you draw your wave, yes, the motion is coming towards the solid barrier. So again, imagine that you're at the pool and the wave hits the edge there, and you're able to make waves if you want to, just even with one of those like flotation devices too. I often do it with the big long chairs that you can just rest in. Anyways, on the way back, what you do notice is that on this side here, the wave is of the same magnitude here. It's just in the opposite form here. It's being reflected in the opposite direction here. Equal but opposite. And that's what happens when you come across something with a solid barrier here. Now for the free end side, and again, if you ever need to pause, just pause so that you can draw what you need to draw and then continue. Here there's nothing attaching the end of this string, and so as the wave propagates to the right over here, what ends up happening is that as it gets the free end there, now the direction of the motion is just coming back in the opposite direction on the same side. And that's for a free end reflection. You're familiar with this website right over here. And so if we take a look, we have a fixed end. Let's set one pulse here. And why not? Let's just increase the amplitude a little bit. As you noticed, once it hit the fixed end here, it reflected, but it was on the opposite side right over here. Now, what you also notice is that the amplitude of the wave decreases, and there's going to be some energy lost within the system, and so that's going to happen. If you were to decrease this to zero dampening, where no energy is lost, then you notice that you're going to have the same magnitude the whole time, but that's just not going to be true in reality. So in reality, when you do have a little bit of dampening, there is some energy lost. You notice that the magnitude decreases over time, or the amplitude does. That's for a fixed end. As for a loose end, so it's a little bit different than no end. So as for the loose end, it's allowed to travel freely, and as it does such, it actually comes up top and then comes back down, and it's able to reflect on the same side as it was propagated in the first place. So we can do a slow motion one, just to take a quick look at what that is. So it's coming to the loose end here, it's coming up, and then it's coming back down, but it reflects in the same side as it first propagated. So we already kind of mention this a little bit, but the reflection energy, uh, so when the pulse is actually reflected, like I said, some of it was lost, and that can be due to heat and friction. And we also noticed that the pulse was smaller than the actual incident pulse, than the first pulse that first was propagated or sent along on its way. If we're looking at different materials, this is on the next page here, if a pulse travels from one medium to another, the velocity changes, but the frequency remains the same. And just think about that for a moment. If you were to have frequency changing depending upon the medium that it's in, that could create some serious problems specifically for sound. And I looked up a little something for sound, and here is what I found here. The perception of frequency is actually called pitch. And the wavelength of sound is not directly sensed, but indirect evidence is actually found in the correlation of the size of musical instruments with their pitch. So we're mostly familiar with this. Small instruments like a piccolo would typically make high-pitched sounds, while large instruments, more like a tuba, would make low-pitched sounds. High pitch means small wavelength. So I'll reiterate that. A high pitch means small wavelength, and the size of the musical instrument is directly related to that wavelength of sound it produces. So a small instrument creates short wavelength sounds. Similar arguments hold that a large instrument creates long wavelength sounds. So we're looking at the speed of sound in a medium. It's determined by both the combination of the medium's rigidity, slash like how compressible it is in gases, as well as its density. So the more rigid it is, or less compressible the medium, the faster the speed of sound. So if something is able to be compressed a lot, such as air, you're going to find that the speed of sound is a lot slower in air, what we breathe, compared to a lot of other gases out there. If there was gases that were unable to be compressed as much, then you're going to find that the speed of sound is going to be a lot larger. And if we're looking at liquids and solids for propagating sound, for example, or sending it on its way, since solids and liquids are relatively rigid and are very difficult to compress, the sound at a speed is often a lot greater than in gases. And what we notice is that for the speed of sound in air, it's usually about 330 approximately meters per second. Meanwhile, in something like hydrogen, it's 1,290 meters per second. So it's approximately 4 times as quick in hydrogen gas as it is in air. So we would recognize that in hydrogen gas, you're unable to compress it the same as you would in air. As for liquids, if we look at seawater, for example, it's even faster. It's at 1,540 meters per second. And seawater versus freshwater is actually a little bit less at 1,480 meters per second. And if you want to look at something that's on the complete other spectrum, so when we're talking about like if you want to dampen a sound wave, you're going to be finding something that is like an insulator. So in the example of vulcanized rubber, you're only going to find sound travels at about 54 meters per second. So much slower than some of those other examples there. One last thing here too, and that's earthquakes. I was reading up on this too a little bit, and they're essentially sound waves in the Earth's crust. And there's actually an interesting way in which they partially help to determine where the origin of the earthquake is. I'm sure there's all kinds of other ways they use as well. But going back to lesson 1, earthquakes do have both longitudinal and transverse components, and these travel at different speeds. So the bulk modulus of granite is greater than its shear modulus. So they're going to be traveling, these waves will travel at different speeds, whether it's in granite or shear or otherwise. And so for this reason, the speed of longitudinal or pressure waves, and they call them P waves in earthquakes, in granite is significantly higher than the speed of the transverse or shear waves. And both components of earthquakes travel slower in less rigid material, such as sediments. And this is very similar to what we were talking about before, how rigid is the medium in which the sound waves are traveling. P waves have speeds between 4 to 7 kilometers per second, while S waves travel close to 2 to 5 kilometers per second, both being faster in more rigid material. The P wave gets progressively farther ahead of the S wave as they travel through Earth's crust, and because of that time difference, they're often able to determine what the distance is from the source, the epicenter of the earthquake. And so it goes from there. So I don't know, just a little interesting random piece of information. Anyways, back to this. Frequency doesn't change, remains the same. Therefore, the wavelength must also change. So if velocity changes, wavelength must also change, because if you're looking at the formula, velocity is equal to frequency times the wavelength. So if velocity increases, the wavelength has to increase. If velocity decreases, the wavelength has to decrease. And so when we're looking at these general rules here, you have, in a less dense medium, the higher wave velocities, it's going to be traveling faster. You're also going to have longer wavelengths. When you have traveling in a more dense medium, you're going to have lower wave velocities, and you're going to have a shorter wavelength as well. So here's the example. If a wave travels from water into jello, we might observe something like this. So a velocity 4 meters per second, a certain frequency, etc., etc. And so you're able to determine, say, what the wavelength is based on this other information. You just plug in the values and then solve. So if you're going from water to jello, the speed changes. I don't have this on the PowerPoint, but it goes from 4 to 3 meters per second. And the frequency stays the same, so it stays at 2 hertz. But if the velocity changes from 4 to 3, we know that the wavelength is also going to have to decrease in distance if the frequency must remain the same. And so what ends up happening is that your wavelength is going to be going from 2 to 1.5 if you plug in your values into the formula. Now, I'm going to quickly go through this first part, and then we're going to look at another website. So, transmission is when the wave continues forward from one medium into another. And so I worded here is when a pulse moves from one medium to another, 2 things happen. First of all, the pulse is transmitted into the new medium, and so that means that the pulse continues onward. And the second thing is that the pulse is partially reflected in the old medium. So part of the pulse is reflected as the majority of the pulse continues and is transmitted into the new medium. Because of this, the energy in the pulse is split between the transmission and the reflection. And so you can already begin to question and ask yourself, what's happening to the wavelength as it transmits into this new medium? What happens to the velocity? What happens to the amplitude? And this can be for the transmitted wave as well as the reflected wave. So please begin to ask these questions as we look at them. Before filling out any of the table, I want you to take a good hard look at what is actually happening in 2 different scenarios here. And so the first scenario is you're going from the high speed to the low speed, or a low density medium to a high density medium, and that's the way that I worded it, at least on the table there. But you can look at it in both ways, because if we noticed before, in the low density medium, what you're going to have is higher wave velocities. And so I already posed some of these questions. Let's take a look again. I want you to actually critically think this through here. This animation has the incident wave, that's this first wave right over here, and it's traveling from a low density, aka high wave speed region, towards a high density, low wave speed region. So please take a moment here. How do the amplitudes of the reflected and transmitted waves compare to the amplitude of the incident wave? So you have the original wave here. What's the amplitude? Now, what's the amplitude of the transmitted wave as well as the reflected wave in comparison to this incident wave? Once you have an answer for that, then move on. How do the polarities of the reflected and transmitted waves compare to the polarity of the incident wave? And I believe by polarity they mean, well, what's the direction of that it's traveling here? Is it in the same side of the string? Like if we want to go north south, is it still on the northern side here, or is it now on the southern side here? And so when it's reflected and when it's transmitted, what's going on here? So we notice that the reflected wave is inverted while the transmitted wave maintains, which if we want to use that terminology, the same polarity. And lastly, how do the widths of the reflected and transmitted waves compare to the width of the incident wave? So if you can try to kind of picture what the width is of the incident wave, what does it look like when you're transmitting it? What does it look like when you are reflecting it? And even what is the width of this part of the wave partially representing? And if you said wavelength, then you are correct. So that's going to be determining what does the wavelength do as it transmits and reflects from the low density to the high density material. And even with what you're visually seeing here, you could theoretically actually fill out this table. But don't worry, we'll still go through it. Now, on the other side, what happens if we're going from, say, something that's low speed with a high density to something that has high speed with low density? And let's start with all the components here. What's going on in a variety of things here? First of all, what's happening to the amplitude of all three, the reflected wave and the transmitted wave, I guess all two, in comparison to the incident wave. That was the third wave. What's happening to the polarities as well? So as it's reflecting off here, what's happening to the reflected wave? What's happening to the transmitted wave? They're both still on the northern side of the string here, so they're not inverting at all. And lastly, again, what's happening to the wavelength as it travels along here? Is it increasing? Is it decreasing? Is it staying the same? All right, back to the table now. All right, let's go through the table now, and we'll start with this second column right over here. This is very similar to the first example on the last website, where we're having a less dense material and medium go into something that's more dense. And the way that the reflection acts is similar to that of a fixed end, which we had looked at prior to that. As for the reflected pulse, what you're going to find is that the polarity is inverted. It's on the opposite side, so that the southern part, if you want to talk about it that way, it's going to have the same length of a wavelength. It's going to be a little bit smaller in amplitude, or even a lot smaller in amplitude, actually. As for the transmitted pulse, the pulse that continues onward, it's going to be on the same side. It's going to have a shorter wavelength as it goes into the more dense medium. And it too is going to have a smaller amplitude on the size of its wave. Going from something that's more dense to less dense, so this was the second example on that website, and this is similar to what we looked at prior to that. It acts, the reflection acts as a free end, so that when it hits the new medium, it's going to reflect, it's going to be on the same side. It's going to have the same length of wavelength, and it's going to have a smaller amplitude as it returns. As for the transmitted pulse, though, here it's going to be on the same side, just like the prior one was, and you're going to have a longer wavelength. But this time, this is the only one that looks a little bit different here. I tried searching for an hour or two as to reasons why this is, but what I found was we have a little bit of a larger amplitude. I could make guesses as to why, but I don't know. So your guess is as good as mine. If we find some information on that, I'd love to hear about it. All right, and lastly, let's take a look at our example here. So we're going from a fast to a slow medium, so something that has low density to high density medium. And we have the incident pulse traveling towards the right here. And as I already mentioned, we have fast and slow mediums based on the densities of them. And what ends up happening is that the end there acts as a fixed end. And so the reflected wave is going to be inverted, as you see right over here. Next, transmitted pulse continues onward. You see that the amplitude is been decreased, as has the reflected pulse over here too. You notice that the wavelength is also decreased in comparison to over here too. Although remember that this is not the full wavelength. If you want a full wavelength, this is only part of it. You have to go all the way, say if you're going from crest here, you have to go all the way back to crest. That's one full wavelength. At the bottom here, it reads inverted reflection. And what you see is the smaller amplitude for both of these as well. And I already mentioned shorter wavelength for that one. Slow to fast. So running off the bat here, we have a high density slow medium running into a fast medium with a low density. Here's the incident pulse. This is going to act as a loose end right over here, as a free end, so that as it travels on, it's going to continue past. And as you can see here, the wavelength increases in length. The reflection is on the same side here. Please take note of this. I didn't have a chance to edit this. There's a smaller amplitude on this side. This side here should actually be a larger amplitude, so it should be a little bit larger here. So just make note of that, okay? And we're going off of also that the animated video or the animation from the other website too that was indicating that this is actually a little bit larger when you're going from high density to low density, or from the slower medium to the fast medium. And longer wavelength over here. Here the wavelength should be the same length as that over there. All right, that concludes this lesson. Good luck on your assignment.